Now what we're doing, we're going to look at variation. Last time we talked about measures of central tendencies. So what we did last time is how the numbers all congregate around a middle number, a central number. But the example we had last time, we had 3 data sets. They each had the same average. Does that mean all 3 sets are the same? No. What we're looking at here in this section the measures of variation deals with just that. It deals with how the data varies from that central number. How the data behave about the central number. The range of your data set. The largest minus the smallest. How is that different than the mid-range? We don't divide by 2. And so is this number going to be bigger or smaller? And not only that, what do we do? How do we do the top number for the mid-range? We add them. This one, we subtract them. This one finds exactly how far apart are the smallest and largest numbers. So there's how many numbers are between 2 and 50? Right. It's the range. So we take the biggest number minus the smallest. We know that there are 48 numbers between there. This, in connection with everything else we've done so far, we're getting a better picture of how the data is being distributed throughout the whole process. We have the same data set we had last time. This example is saying, find the range of wait times at Space Mountain. So to find the range, what do we have to find? Yes, so what's the largest? minus the smallest. Is it 20? 20. And that equals? Yeah, that's looking at these numbers. These are only two-digit numbers. 55, that's a pretty big range for two-digit numbers. It doesn't tell us much other than that. It just tells us that from the smallest to the largest, it's a big spread of numbers. Let me see if I can find those. So here we have the three paint samples from last time. They all had the same mean, the same average. And the question I asked you all is, which one is the better paint? What we have to look at is to see how far on the average do each of those numbers, how far away from the mean? The smaller the distance they are from the mean, the more accurate the data set is. We're going to use the word standard deviation a lot. And we'll go one step further and talk about standard variance. Oh, I never talked about this first. When we deal with probabilities and statistics, we have two types. We have populations, and then we have samples. Which one's more accurate? Population, yes, because that's the truth. That's exactly what you're looking for. A sample is used because you can't do the population. It's too big, too expensive, whatever. So we do a smaller sample of it. Now, how do you know if you're looking at the information that deals with a population or a sample? In population, we use Greek letters. And our samples are represented by our symbols, our alphabet, A, B, C, D, E, X, Y, Z. The reason that's important because when you present your information, all I have to look at is if I'm looking at they're both telling me the mean, the average, but which one's more accurate? This one, because that's over the population. So whenever you use Greek letters, that is to represent the population information. I should have done that the first day of class. I'm sorry. So that's the difference which we'll be using throughout this course. We'll be using Greek letters or our alphabetic letters. So now, what do you think a standard deviation is? What do you think it does? What does deviation mean? We haven't talked about it yet, so you can't find it. what, have you ever heard the word deviation before? What does it mean? If something deviates, what is it doing? Deviation is how far something is from something else. There's how far, what we're looking at here is how far is our data set away from our average. That's a deviation. So if you had an average data value, if this was your mean, and the rest of your data looked like this, what we're looking for is how far are these numbers away from this average line? That's our ultimate goal in this course. So what we're looking at here now is we're looking individually, each value. So here's our mean. Let's say X1 is up here, X2 is here. So the deviation of X2 is smaller than that of X1. But if you notice, it's on the bottom. So this one's positive, this one's negative. Which one's further away? The top one or the bottom one? The top one looks like it's a bit further away. So, and the more data values we have, we're hopefully that's going to even out. So for the standard deviation, we're going to use the letter S. This is standard deviation of a sample. We have two equations that we're going to be referring to all the time. The summation of x minus x bar squared over n minus 1. That's one formula. Or we could use the more parsed out one, is saying that n times summation of x squared minus the summation of x squared all over n minus 1. So what we're looking at is how far is the data away from the average point, the mean point. Notice the standard deviation can never be negative. Why can the standard deviation never be negative? Can anybody guess? Because of what? That's very true. There's no definition. It's the distance. All distance is always absolute value. It's always positive. But that's very good. That's going by definition of it. But also, can you ever take a square root of a negative number? No. And you notice this number here can never be negative. Because whenever, even if you have a negative number here and you square it, what happens to that number? If you take -2 and square it, what do you get? -2 times -2 is +4. So when you square it, it always comes out to be positive. And these right here, x squared is positive. So when you add up all your positive numbers, the summation of x, positive, it comes out to be positive. So These numbers can never be negative because we're looking at a distance on how far it could be from the mean. So this, can it equal 0? Yes. If all the data points you have is the same as the mean, if they're all the same, the mean's the same, so the distance is 0. So let's look at how we do this calculation. Let's use this set here, the same one we've been using. Well, let's use that. I'll use this because I want to show you how to do this manually first, because okay, you're always going to use a computer or calculator to do these for you anyway. But let's look at these 5 numbers here. Calculate the standard deviation. So we can use 2 formulas. We can use that formula. And then we're going to look at the other formula. If you ever took algebra, we learned that distance is equal to the absolute value of how far the things are apart. It's always an absolute value. Why? Because if you have a value and it's to the right, it's positive, it's to the left, it's negative. But we're looking at how far they are away from each other. What is the formula for absolute value? The formula for absolute value is the square root of x squared. Because if x is positive, let's say x is 3, and I square it, what does that become? 9. And if I square root 9, I get 3. I get what I started off with. If my x is -2 and I square it, what do I get? +4. And I square root +4, I get 2. The distance, how far it is from 0. So that's what the absolute value, and that's why these are set up the way they are. So let's look at this first one. Let's create a table. So we have 25, 35, 50, 50. Let's get our data. I'll make these easier for us, so we don't have to use calculators. So it's 25, 25, 40, 60, 75. So to use this formula, what do we need to know? To use this formula, what do we have to have defined? We have to have the mean. How do we find the mean? Add up your data, which was 100, 200, 225. Divided by n. What is n? The number of points that you have. So n is 5. and we ended up with 45. So that's my mean. Because in your equation, you have to have the mean. You have to know what n is. This x are your data values. So the first thing we have to do in this equation is what? How do we build this equation? What do we have to do first? You have to do x minus x bar, right? So we have to have x minus x bar. Remember, our x bar was 45. So 25 minus 45 is what? Is it positive or negative? Negative 20. This one's negative 20. 40 minus 45 is negative 5. 60 minus 45, that's positive 15. 75 minus 45 is 30. If we add these together, what do we get? Nope. Yep. That's a good sign. Why is that a good sign? Because remember, we're looking at our numbers, how far they are from the mean. These are smaller than the mean, and these are larger than the mean. If I add them together, they all equal out. This has to equal 0. So the distance from all our data to the mean has to equal 0. How do I make it stop being 0? What made it equal 0? These negatives. So how do I get rid of the negatives? I square each one of those. So negative 20 times negative 20 is positive 400. Negative 20 times negative 20 is positive 400. Negative 5 times negative 5 is 25. Fifteen times 15 is 225. 30 times 30 is 900. Now, according to our formula, we have to add them all together. So we got 5 plus 5 is 0, carry the 1. 2, 4, 5, 8, 17, 1950. Great. You notice that's positive, but it's really big. So in our formula, the next thing we have to do is we have to divide by n minus 1. What's n represent? Yeah. So n is 5. So 5 minus 1 is 4. So now we have to take this number and divide by 4. 4 goes into 19 how many times? 4 times 4 is 4 times 4 is 16. So that means there's 3 left over. 4 goes into 35 8 times. 8 times 4 is 32, so that leaves 3 left over. Four goes into 30. 7, that makes 28. So it's 2 left over. So it's 487.5. But it's huge. Because remember, our numbers are pretty small. So why is it so big? Put your phone away. Yes. Why is it so big? What did we do here? We doubled the numbers. We made them much bigger. The reason we did that is to get rid of the negative numbers here. How do we shrink this number? We squared it here. What's opposite of squaring? Square root. So we square it here and we square root it at the end. We inflate it and we shrink it back down. So what's the square root of 487.5? Square root. So it's 487.5 equals 22.08. So this is my standard deviation. What it tells us is on average, all of our numbers are about 22 point, let's make it 22.1. They're approximately 22.1 units away from the mean. That's what it tells us. Remember, the bigger this number is, the further the numbers are from the mean. So let's go back to this example. So in order for us to find out which paint is the best, since they all have the same average, we have to find out which ones have the smallest standard deviation. Because what that would mean, the smaller standard deviation, that could mean that tells you how far from the average your paint is going to last, or could last. So let's go ahead and figure these out. Here are the data. So this part of the room, do column A, the 3 of y'all. The 3 of y'all do column B, and the 2 of y'all do column C. You can work separately, see if you get the same answer at the end.